The first thing you notice is the water. It stretches across the horizon before you, filling the northern lowlands of Mars, in a sea larger than Earth's Arctic Ocean. Tonight, you are standing at the edge of that ocean, on Mars billions of years in the past. The shoreline beneath your feet is real, made of sand and small rounded stones that the waves have shaped over countless years. Behind you, the land rises gently toward the southern highlands, and ahead, the water extends northward into a basin that holds more water than seems possible on a world we know as dry and frozen. The air around you is different from the Mars of modern times, thicker and warmer, substantial enough to feel against your skin. The atmosphere here can support liquid water, and the proof is in front of you in the form of actual waves rolling in from the Northern Ocean. The sky above has a color somewhere between orange and tan, the result of dust suspended in air that is denser than it will be billions of years from now. You are standing approximately 3.7 billion years in the past, during a period scientists call the Noachian, when Mars was a different world. You are listening to the Drowsy Astronaut, and this is a slow journey through ancient Mars when liquid water covered much of the northern hemisphere. We are going to walk the shores of this vanished sea and explore the valleys that fed it, and understand what happened to all that water. If you are still awake later, feel free to share where you are listening from in the comments. And if this kind of gentle exploration through deep time appeals to you, consider subscribing or even joining as a member to support more journeys like this. For now, we are here at the boundary between land and sea, on a Mars that has not existed for billions of years. The water in front of you is dark, darker than Earth's oceans because of different chemistry and the suspended sediment it carries from rivers flowing into it. Small waves break against the shore in a rhythm that feels familiar despite the alien setting, and the physics of water and wind are the same here as they are on any world with liquid and atmosphere. The wave height is modest, perhaps half a meter or less, and they roll in steadily from the north, where the ocean extends for thousands of kilometers. The sound of water meeting land is quieter than it would be on Earth, because the air is thinner even in this ancient, thicker state, but you can still hear it. Looking down at the shoreline itself reveals details that confirm this is a real coast shaped by real water over immense time. The sand beneath your boots is sorted by size, with finer material closer to the current water level and coarser pebbles farther up the beach slope. This sorting happens through wave action, as water picks up and deposits material based on particle size and weight. And it creates patterns that geologists recognize instantly as evidence of coastal processes. The stones are rounded from tumbling in the waves, their sharp edges worn away by countless collisions with other rocks over millions of years. The temperature is cool but not freezing, perhaps around 5 or 10 degrees Celsius, well above the point where water turns to ice. The thicker atmosphere provides greenhouse warming that keeps the surface warm enough for liquid water to persist, at least in this region and during this time period. The atmospheric pressure is substantial enough that water can exist in its liquid phase without boiling away into vapor or freezing into ice, conditions that modern Mars cannot provide. You are experiencing Mars during a window of time when the planet was habitable for water, if not for life as we know it. Turning to look south, you can see where the land rises from the lowlands toward the highlands that dominate Mars's southern hemisphere. The elevation difference between where you stand and the highland terrain is enormous. Approximately 4 to 5 kilometers of vertical drop from the southern uplands to this northern basin. The ocean fills the low area created by this ancient topographic dichotomy, with water naturally flowing downhill and collecting in the deepest available basin. The boundary between the wet lowlands and the dry highlands creates this shoreline, a contact zone that runs for thousands of kilometers around the northern basin. The region where you are standing has a name in the modern study of Mars, though the ancient inhabitants, if any existed, would not have called it anything. This is the Arabia shoreline contact, one of 2 main shoreline levels that scientists have identified in satellite data and elevation mapping of modern Mars. The Arabia contact sits at a higher elevation than the other shoreline, called Deuteronilus, suggesting that the ocean had different water levels at different times in Mars's history. You are observing the ocean during one of its higher stands, when water filled the basin more completely. Looking east and west along the shore, you can see the shoreline extending in both directions beyond the limits of vision. The curvature of Mars is less than Earth's because Mars is smaller, about half Earth's diameter, but the horizon is still several kilometers away, and the shoreline continues far beyond it. This is not a small lake or a localized sea, but rather a planetary-scale ocean that wraps around Mars's northern hemisphere. The total area covered by water is larger than the Arctic Ocean on Earth, perhaps 1.6 times the Arctic's area. Walking forward until the water reaches your boots allows you to feel the temperature of the ocean directly, and it is cold, perhaps just a few degrees above freezing. The water is not tropical or even temperate, but rather a cold polar or subpolar sea, chilled by the distance from the sun and the limited greenhouse warming available even with the thicker atmosphere. Mars orbits farther from the sun than Earth does, about 1.5 times Earth's orbital distance, and the sunlight here is only about 40% as intense as sunlight at Earth's distance. The reduced solar energy means Mars is fundamentally colder than Earth, even with atmospheric help. Water flowing from the highlands would carry dissolved minerals from rocks, and those minerals would accumulate in the ocean over millions of years, just as they do in Earth's seas. The salinity might affect the freezing point, allowing the water to remain liquid at temperatures slightly below 0 Celsius. The chemistry of this ancient ocean is one of the many questions that scientists continue to study through analysis of Martian rocks and minerals. Crouching down to examine the beach more closely reveals additional details about how this shoreline formed and persisted. Small ripple marks are visible in the sand, frozen patterns created by the last waves that moved across this spot before you arrived to observe it. The ripples point in a direction that indicates the wave approach angle, and they show that water has been actively shaping this beach recently. Between the ripples, tiny fragments of rock and mineral crystals catch the light, each one a piece of Mars's crust broken down by weathering and transported here by water. Standing again and looking out across the water, you can try to grasp the scale of what you are seeing. This ocean contains an enormous volume of water, enough that if it was spread evenly across all of Mars, it would create a layer 100 to 200 meters deep, covering the entire planet. The actual ocean is much deeper than that in places, because the water is concentrated in the northern lowlands basin rather than spread globally. Depth measurements suggest the deepest parts of the basin might hold water, 1.6 kilometers deep, though the average depth is less, and many areas near the shore are shallow. The evidence for this ocean's existence comes from multiple sources that scientists have pieced together from studying modern Mars. Elevation mapping from orbiting spacecraft shows that the northern lowlands sit consistently lower than the southern highlands, creating a natural basin. The shoreline features run along lines of consistent elevation, exactly as shorelines should if they were shaped by water seeking a level surface. Minerals detected from orbit include clays and other compounds that form through water alteration of rocks. Valley networks visible across the highlands all drain toward the northern lowlands as if feeding water into a collecting basin. The time period you are experiencing is called the Noachian, after Noachi's Terror, a region in the southern highlands. The Noachian extended from about 4.1 billion years ago to about 3.7 billion years ago, spanning roughly 400 million years of Martian history. This was the period when Mars was most Earth-like, with substantial water on the surface and an atmosphere thick enough to support it. What you are seeing is Mars during its wet phase, before the changes that would eventually transform it into the frozen desert we know today. Above you, the sky shows variations in brightness and color that suggest weather patterns are active in this ancient Martian atmosphere. Clouds are visible in the distance, likely composed of water vapor that is evaporated from the ocean and condensed at higher altitudes. The presence of clouds indicates an active water cycle with evaporation, condensation, and potentially precipitation. Rain may fall in some regions, feeding the valley networks that drain into the ocean and maintaining the water volume despite losses to space and ice. The waves continue their steady rhythm against the shore, each one carrying energy from wind blowing across the ocean's surface. The wave patterns suggest that wind is present and strong enough to generate surface waves, which requires substantial atmospheric density. The wind direction appears to be from the north, pushing water toward the southern shore where you stand. The distance over water that wind can act upon is enormous because the ocean extends for thousands of kilometers to the north. Long fetch allows waves to build to larger sizes, though the waves here remain relatively small compared to Earth's stormier seas. Walking along the ancient Martian shoreline takes you parallel to the water's edge, and the beach stretches ahead for as far as you can see in both directions. The sand beneath your feet changes texture as you walk, sometimes fine and smooth where recent waves have reworked it, sometimes coarser where larger stones accumulate. Each step leaves a footprint that fills partway with water seeping up from below, showing that the sand is saturated just beneath the surface. The sound of your movement is muted in the thinner atmosphere, but the crunch of sand and the occasional scrape of stone against stone are still audible. The shoreline is not perfectly straight, but instead shows gentle curves and irregularities that follow the underlying topography of the basin edge. In some areas, the beach widens to form broad, flat zones where fine sediment has accumulated, while in other places, the beach narrows where harder rock resists erosion and forces the shore into a more constrained space. These variations create a natural complexity along the coast, a pattern that would be familiar to anyone who has walked along Earth's shorelines. The same physical processes that shape beaches on Earth have been operating here for millions of years. Looking to your right toward the ocean, you can see how the watercolor changes with depth. Near the shore, the water appears lighter, perhaps showing the sandy bottom through the clear, shallow water. While farther out, it darkens to a deeper blue-grey or greenish-grey as the depth increases, beyond where light penetrates to the bottom. The color gradient provides a visual indication of how the basin floor slopes downward from the shore toward the deeper ocean interior. Waves breaking in the shallow water create white foam occasionally, especially where underwater features cause the waves to steepen and collapse. To your left, the land rises in a gradual slope away from the water's edge, and you can see beach ridges at higher elevations marking previous shoreline positions. These ridges are parallel to the current shore and represent times when the water level was higher, either because more water was present in the ocean or because the land was lower relative to the water surface. The ridges are subtle, perhaps only half a meter to a meter in height, but their linearity and regular spacing mark them clearly as features created by wave action at former water levels. The beach material shows sorting patterns that reveal how water moves sediment based on size and density. Closer to the current waterline, the particles are predominantly fine sand mixed with some silt, material that water can easily transport and deposit. Farther up the beach, away from the water, the material becomes coarser, with more pebbles and small cobbles mixed among the sand. This inverse grading happens because larger particles require more energy to move, and they get deposited higher up the beach during larger waves or storm events. The pattern has built up over many years as countless waves have reworked the sediment. Walking farther along the shore brings you to an area where a small stream enters the ocean, cutting through the beach and creating a miniature delta where the stream deposits its sediment load as the current slows upon meeting the ocean. The stream is perhaps 2 or 3 meters wide, shallow enough to wade across, and it flows steadily from the highlands behind you toward the water ahead. This stream represents one of thousands of water sources feeding the ocean, part of a network of valleys that drain the southern highlands and carry water downslope to the northern basin. The delta, where the stream meets the ocean, shows fine layering in the deposited sediment, each layer representing a period of deposition followed by a pause. The layers vary in thickness and grain size, depending on how much water the stream was carrying and how fast it was flowing when each layer formed. Some layers are finer, deposited during low flow when the stream carried mainly silt and clay. Others are coarser with visible sand grains, deposited during higher flow when the stream had more energy to transport larger particles. The entire structure demonstrates that this stream has been flowing for a substantial time, long enough to build a noticeable accumulation of sediment. Stepping across the stream allows you to continue walking along the shore toward an area where the beach transitions into a rocky coast. Here, the beach sediment gives way to exposed bedrock, ancient Martian crust that forms the foundation beneath the sedimentary layers. The rock is weathered and fractured, with surfaces that show the effects of water action over geological time. Wave-cut notches are visible at the current water level, places where waves have preferentially eroded softer layers or exploited existing fractures to carve into the rock. The notches create small overhangs and sheltered spaces that would protect these areas from direct wave impact. The rocky coast shows different erosion patterns than the sandy beach, and you can see how resistant and less resistant rock layers create an irregular coastline. Harder rocks protrude as small headlands that extend into the water, while softer rocks erode back to form small bays and indentations. The differential erosion creates a complex three-dimensional coastal topography, with pools of standing water trapped in depressions at low tide and exposed rock platforms that extend into the ocean. The platforms are covered with a thin coating of algae or mineral precipitate, giving them a slightly different color than the rock above the waterline. Pools trapped between rocks contain seawater that has been isolated from the main ocean by the falling tide, and peering into one of these pools shows water that is very clear despite the cold temperature. Small particles of sediment rest on the bottom, having settled out when the water stopped moving, and tiny bubbles of gas cling to the rock surfaces. The gas is likely dissolved air, coming out of solution as temperature or pressure changed. Though without life in this ocean, there are no biological sources of gas, like photosynthesis, that would be present in Earth's tidal pools. Continuing along the rocky shore takes you past areas where the bedrock shows clear layering, with beds of different rock types stacked on top of each other. Some layers are reddish, colored by iron oxides that form when iron-bearing minerals are exposed to water and oxygen, while other layers are gray or tan, showing different mineral compositions. The layering represents different episodes of deposition or volcanic activity in Mars's ancient past, times when sediment accumulated on the surface or lava flows spread across the landscape. The layers have been tilted slightly from horizontal, perhaps by ancient tectonic forces or by the weight of later deposits pressing down on them. Wave-cut benches are visible at several elevations along the rocky coast, each bench representing a time when the water level was stable enough for waves to erode a flat platform into the rock. The benches sit at different heights, with the highest ones representing the highest water levels the ocean reached, and the lowest ones representing times when the ocean was shallower. The existence of multiple benches indicates that the ocean level changed over time, rising and falling as water was added by rainfall and rivers, or removed by evaporation and freezing. Each bench took thousands or millions of years to form, because rock erosion by waves is a slow process even in the most favorable conditions. Looking south from the rocky coast, you can see the terrain rising more steeply here than in the sandy beach areas, with slopes that climb toward the highland interior. The steep slopes are cut by small gullies where rainwater or snowmelt has carved channels on its way down to the ocean, and some of these gullies still carry water in small streams similar to the one you crossed earlier. The vegetation-free landscape shows the rock and soil clearly, with no plants to obscure the geological details. The colors are predominantly reds and browns from iron-rich minerals, with some grays and tans where different rock types are exposed. The beach material accumulated at the base of the rocky cliffs shows a mix of angular fragments that have broken off the cliff face and rounded pebbles that have been transported by water and worn smooth. The angular fragments are fresh, showing sharp edges and unweathered surfaces, while the rounded pebbles are older and have spent more time being moved by waves and streams. The mixture indicates that both cliff erosion and sediment transport are active processes here, with the beach receiving material from multiple sources and reworking it continuously. Over time, the angular fragments will become rounded as they are tumbled by waves against other rocks. Further along the shore, you encounter a section where large boulders rest on the beach, each one several meters across and weighing many tons. These boulders are too large for normal waves to move, and their presence here suggests that either they fell from nearby cliffs or they were transported during exceptional events, like unusually large storms or ancient catastrophic floods. The boulders show weathering on their surfaces, with cracks and flaking that indicate they have been exposed to water and atmospheric conditions for a very long time. Some have accumulated fine sediment in their lee, deposited in the sheltered area behind the boulder where wave energy is reduced. Standing next to one of the large boulders and looking back the way you came, the shoreline extends into the distance, showing all the variations you have walked past. Sandy beaches alternate with rocky coasts. Streams enter the ocean through small deltas, and the water continues its steady presence, filling the northern lowlands. The ancient Martian Ocean is real and substantial, a body of water that has shaped this coastline through processes operating over millions of years. The evidence is everywhere, in the sorted sediments, the eroded rocks, the beach ridges, and the wave-cut features that mark the boundary between land and sea. Turning away from the immediate shoreline and walking inland brings you to higher ground, where the terrain begins its gradual rise toward the southern highlands. The slope is gentle at first, perhaps only a few degrees, but it increases as you move farther from the ocean basin. Beneath your feet, the ground changes from beach sand to more consolidated soil and exposed bedrock, material that has not been reworked by recent wave action. Small plants or lichens would make sense in this environment if life existed, but the landscape appears barren, showing only rock, soil, and occasional patches of frost in shadowed areas. The valley you are approaching cuts through this rising terrain, a channel perhaps 50 meters wide at this point and several meters deep below the surrounding surface. The valley floor is relatively flat and smooth, showing the characteristics of a channel shaped by flowing water over extended time. The walls on either side rise in slopes that vary from gentle to steep, depending on the local rock strength and structure. At the valley bottom, a stream flows steadily, the same kind of stream you crossed earlier near the coast. But here, you can see it in its upstream context, draining water from the interior highlands toward the ocean. Walking down the slope into the valley brings you to the stream's edge, and you can observe the water as it moves past. The current is moderate, fast enough to move sand and small pebbles along the bottom, but not torrential or turbulent. The water appears clear near the surface, but shows brownish color near the bottom, where it picks up sediment from the bed. The stream depth is perhaps half a meter in the middle, shallow enough to wade across, but deep enough to sustain continuous flow. The width varies from 3 to 5 meters, depending on where you measure it, wider in straight sections and narrower where the channel bends. Following the valley upstream takes you away from the ocean and into the highland terrain, and the valley's character becomes more apparent as you walk. The channel shows meandering curves that snake back and forth across the broader valley floor, a pattern that forms when flowing water erodes the outside of bends and deposits sediment on the inside of bends. The meanders indicate that the stream has been flowing here for a very long time, long enough for the channel to develop these characteristic sinuous curves through countless minor adjustments in flow path. Flash floods or catastrophic events would create straight channels, but sustained gentle flow creates meanders. The valley walls show layering similar to what you saw on the rocky coast, with different colored beds stacked on top of each other. Some layers are more resistant to erosion and protrude from the wall as small ledges, while softer layers erode back to form recesses and slopes. The resistant layers often cap the valley walls, protecting the softer material below from eroding away completely. Water seeping from some layers indicates that groundwater is present in the subsurface, flowing through porous rock units until it encounters the valley wall, where it emerges as small springs that feed the main stream. Smaller tributary valleys join the main valley from both sides, each one carrying its own stream down from the surrounding highlands. The tributary valleys are narrower and shallower than the main valley, showing that they carry less water and have eroded less deeply into the landscape. Where tributaries join the main valley, you can see small deltas or alluvial fans, where the tributary streams deposit sediment as they slow down upon meeting the flatter main valley floor. The network of tributaries spreading across the landscape resembles the branching pattern of a tree, with larger branches splitting into smaller ones as you trace them upstream. The gradient of the valley floor is gentle but consistent, perhaps 1 or 2 degrees of slope, enough to maintain stream flow, but not so steep that the water becomes a rushing torrent. The gentle gradient suggests that erosion has been operating for a very long time, wearing down the initial steeper slopes into a more mature profile. Young valleys tend to be steep and V-shaped, while old valleys become gentler and wider as erosion progressively lowers the landscape. This valley shows characteristics of maturity, with wide floor and gentle slopes indicating millions of years of development. Walking farther upstream, you pass areas where the stream has exposed bedrock in the channel floor, and you can see how the flowing water has sculpted the rock surface. Smooth curves and bowl-shaped depressions show where persistent currents have worn away the rock grain by grain over immense time. Small potholes appear where rocks trapped in depressions have been swirled around by currents, grinding the pothole deeper with each rotation. These features form only under sustained water flow, requiring years or centuries of continuous stream activity to carve noticeable marks in solid rock. Sediment bars are visible at intervals along the stream, built up on the inside of meander bends, where the current slows and deposits material. The bars are composed of sorted sediment, with the coarsest material near the stream channel and finer material toward the edges. Some bars have become stable enough that fine sediment and dust have accumulated on their surfaces, creating flat areas that only flood during the highest water levels. The bars shift and change over time as the stream adjusts its course, but the pattern of deposition on the inside of bends remains consistent. The surrounding landscape visible from the valley bottom shows more valleys in the distance, each one cutting through the highlands and trending generally northward toward the ocean. The valleys are spaced irregularly, depending on local topography, and the locations where rainwater or groundwater naturally concentrates before flowing downhill. Some valleys are deeply incised with steep walls, while others are broader and shallower. The entire region is dissected by this network of valleys, all of them feeding water from the highlands into the northern lowlands, where the ocean collects it. Looking at the valley walls more closely reveals that they are composed of many thin layers rather than massive, uniform rock. Each layer represents a different depositional event in Mars's distant past. Perhaps volcanic ash falls, wind-blown dust accumulations, or water-deposited sediments from ancient floods or lakes that existed before this valley formed. The layers are approximately horizontal, showing that they were originally deposited on a flat or gently sloping surface, and the valley has cut down through them like a knife cutting through a layer cake. The cross-section exposed in the valley walls provides a record of Mars's geological history, spanning potentially billions of years. Some layers contain rounded pebbles or cobbles embedded in finer material, indicating that those particular layers were deposited by flowing water rather than by wind or volcanic processes. The pebbles are too heavy for wind to move, so their presence requires water currents strong enough to transport them. These conglomerate layers suggest that ancient floods or rivers predated the current valley and stream system, showing that water has been active in this region for multiple episodes in Mars's history. The current stream is just the latest in a long sequence of water activity. Continuing upstream brings you to an area where the valley splits into multiple branches, each branch draining a different part of the highlands. The branches are smaller than the main valley, showing the dendritic pattern typical of rainfall-fed drainage systems. Water, falling as rain on the highlands, flows downhill through the smallest channels, and these merge into progressively larger channels as you move downstream, eventually forming the main valley you have been following. The pattern is identical to terrestrial river systems, demonstrating that the same physical principles govern water flow regardless of which planet you are on. The stream flow appears steady and consistent, suggesting that the water source is not just occasional rainfall, but also groundwater discharge from springs and seeps in the valley walls. Groundwater systems require time to develop, with water slowly percolating through porous rocks and accumulating in underground reservoirs called aquifers. The aquifers feed the stream through springs, providing base flow even during dry periods when rain is not falling. The combination of rainfall runoff and groundwater discharge maintains the stream through varying conditions, ensuring continuous flow year after year. Reaching a point high in the valley where you can look back downstream shows the path you have walked, the valley descending gently toward the distant ocean. From this elevation, the northern lowlands are visible as a flatter, darker region in the distance, the ocean's surface catching light and appearing as a subtle brightening at the horizon. The elevation difference between your current position and the ocean shore is perhaps 1 or 2 kilometers, and the valley has provided a gradual route between these elevations. The view encompasses the entire drainage system from highlands to ocean, showing how water connects different parts of ancient Mars into a unified hydrological system. The age of these valleys is considerable, with formation beginning perhaps 3.9 or 4 billion years ago and continuing for hundreds of millions of years, as long as the climate supported flowing water. The valleys preserve their form despite this great age because erosion on Mars has been minimal since the water stopped flowing. On Earth, tectonics and weathering would have erased or heavily modified such features, but Mars's geological quietness has preserved them like fossils, allowing modern orbital cameras to see patterns carved billions of years in the past. The valley you are standing in is both ancient and remarkably well preserved, a window into Mars's wet history. Walking down out of the valley system and onto the broad northern plains brings you into a completely different landscape, one dominated by flatness rather than by valleys and slopes. The northern lowlands of Mars extend in all directions around you, a vast basin that stretches for thousands of kilometers and encompasses roughly 40% of the planet's surface area. The ground beneath your feet is smooth and level, lacking the rocks and irregularities of the highland terrain you left behind. Fine sediment covers the surface, material that has been deposited by water settling in this low-lying basin over millions of years. This is the floor of the ancient ocean, the basin that held water when the northern lowlands were flooded. The sediment beneath you was deposited underwater, settling slowly through the water column and accumulating in layers that eventually filled the basin to its current level. The smoothness of the terrain reflects the way water-deposited sediment creates flat surfaces, with each layer spreading evenly across the available area before the next layer begins. The lack of major relief features means you can see for many kilometers in all directions, limited only by the curvature of the planet and the haze in the atmosphere. Looking around from this vantage point on the basin floor, you notice that the terrain is not completely featureless, despite its overall smoothness. Subtle undulations rise and fall over distances of hundreds of meters, creating gentle swells in the landscape that would be invisible from ground level, but become apparent when you observe the horizon's position relative to nearby features. These undulations might represent underlying topography that was not completely buried by sediment, or they might be features created by sediment deposition patterns, such as underwater dunes or ripples formed by bottom currents in the ancient ocean. The elevation of where you stand is approximately 4 kilometers lower than the average elevation of the southern highlands, and this difference is what created the basin that collected water in the first place. Gravity causes water to flow downhill, and on a planetary scale, this means water accumulates in the lowest available basins. The northern lowlands represent Mars's largest topographic low, and all the water flowing from the highlands through the valley networks eventually ended up here. The basin was like a planetary bathtub, with the highlands forming the rim and the lowlands forming the basin interior. The origin of this elevation difference between north and south on Mars is one of the planet's great geological mysteries, often called the crustal dichotomy or the hemispheric dichotomy. The southern highlands are heavily cratered, ancient terrain similar to the Moon's highlands, while the northern lowlands are smoother, younger terrain with far fewer large craters. The boundary between them is remarkably sharp in some places, with the elevation dropping rapidly over relatively short distances. Scientists have proposed several explanations, including a giant impact early in Mars's history or internal mantle convection that thinned the crust in the north. But the exact cause remains uncertain. Walking across the basin floor, you can feel how different the surface is from the beach or valley areas you explored earlier. The sediment here is very fine, almost powder-like in places, composed of silt and clay particles that settled out of calm water far from the shore where wave action could not reach. The material compresses slightly under your weight, but then holds firm, showing that it is densely packed despite its fine texture. The color is a uniform reddish-brown, the result of iron oxides coating the sediment particles and giving Mars its characteristic red appearance. The smoothness of the surface suggests that when this area was underwater, it was a region of quiet deposition rather than energetic currents. Storm waves might have stirred up sediment near the shore, but here, in the deeper basin interior, the water would have been calmer most of the time. Sediment settling through still water creates flat horizontal layers that accumulate slowly but steadily over geological time. The thickness of sediment in the northern lowlands might be hundreds of meters in some locations, representing millions of years of continuous deposition while the ocean existed. Scattered across the smooth plains are occasional rocks that protrude from the fine sediment, appearing as isolated fragments in the otherwise uniform surface. These rocks might be meteorites that fell into the ancient ocean and sank to the bottom, or they might be pieces of Mars's bedrock that were transported here by ice or unusual currents. Each rock is out of place in this sediment-dominated environment, standing out visually because of its size and different texture. The rocks show weathering on their surfaces, with rounded edges and pitted textures that could result from either water action or from billions of years of exposure to the Martian atmosphere after the ocean disappeared. The horizon in every direction shows the same flat terrain extending to the limits of visibility, and the sense of vast open space is profound. On Earth, even large flat areas like prairies or deserts usually have some distant mountains or hills to break the horizon. But here the flatness continues until atmospheric haze and planetary curvature make distant features invisible. The scale of the northern lowlands is difficult to comprehend because the human brain expects more variation, but this basin covers an area larger than some of Earth's oceans. And much of it has this same flat character. Looking down at your feet and brushing away the surface dust reveals that just beneath the top layer, the sediment shows faint layering. The layers are thin, perhaps only millimeters thick, and they vary slightly in color and grain size. Each layer represents a distinct depositional event, a period when sediment with particular characteristics settled to the ocean floor. The layering proves that deposition happened episodically rather than continuously, with pulses of sediment delivery from rivers or from material suspended in the water column, settling out during calm periods. The layers are horizontal and parallel, showing that the ocean floor was relatively stable and that currents were not strong enough to erode or distort the layers after they formed. Some areas of the basin floor show what appear to be low ridges that trend in consistent directions across the landscape. The ridges are subtle, rising only a meter or two above the surrounding surface, but their linear arrangement suggests they are not random features. They might represent underwater features such as sand waves or mud ridges that formed under the influence of bottom currents in the ancient ocean. Alternatively, they could be wrinkle ridges, tectonic features that form when the surface compresses slightly and buckles upward. Distinguishing between these possibilities would require close examination, but the presence of organized linear features shows that the basin floor has not remained completely static. The weather here on the basin floor seems calmer than it was near the shore, with less wind and more stable conditions. The distance from the ocean's current position might explain this. Or perhaps the basin interior has naturally more settled atmospheric conditions. The sky above remains hazy, orange-tan, and you can see clouds in the distance, moving slowly across the horizon. The temperature is cool, similar to what you experienced at the shore, maintaining the conditions necessary for liquid water to exist somewhere in this ancient environment, even if not right here at this moment. Walking several more kilometers across the basin brings you to an area where the surface changes slightly in character, becoming darker and showing what might be differences in mineral composition. The darker material could be volcanic in origin, perhaps an ancient lava flow that spread across the basin floor before the ocean formed and is now buried under a thinner layer of sediment. Mars has extensive volcanic features, and the northern lowlands contain several large volcanic structures, including the Tharsis volcanoes and Olympus Mons, though those features are farther west and south of your current position. Volcanic material in the northern lowlands would have interacted with water if it was erupted while the ocean existed, creating different rock types than dry volcanic eruptions produce. The vastness and flatness of this basin emphasize how much water would have been required to fill it. Estimates suggest that the ocean contained a volume of water equivalent to what would cover the entire planet to a depth of 100 to 200 meters, if spread evenly across Mars's surface. The actual ocean was much deeper than that in places, because all that water was concentrated in the northern lowlands rather than being distributed globally. The deepest parts of the basin, in areas even lower than where you currently stand, might have contained water more than 1.5 kilometers deep. Modern Mars observations have revealed mineral signatures across the northern lowlands that are consistent with water alteration of rocks. Phyllosilicates, which are clay minerals that form when water interacts with volcanic rock, have been detected from orbit in some regions. These minerals form through chemical reactions that require liquid water to proceed, and their presence supports the hypothesis that this basin once held water. Other minerals, including sulfates and carbonates, have also been identified, showing that the chemistry of the ancient ocean was complex and involved multiple elements beyond just hydrogen and oxygen. Looking back toward the south, the highlands are visible in the distance as a subtle change in the horizon's height and character. The highlands rise above the basin rim, their elevation marking the boundary of the ocean's extent during its maximum stand. From this position deep in the basin interior, the elevation difference is not dramatically apparent because the distance softens the contrast. But you know from walking down the valley that the highlands sit kilometers higher than the basin floor. The water that filled this basin would have been deepest here and shallower near the edges, creating a natural depth gradient from basin center to basin margin. The time you are experiencing is still the Noachian period, when Mars's climate permitted liquid water to persist on the surface. This ocean has existed for millions of years already, and will continue to exist for perhaps hundreds of millions of years more before the changing climate forces it to retreat and eventually disappear. For now, though, the basin is a sea floor, and the evidence of that will remain even after the water is gone. The sediments will harden into rock, the surface will be exposed to space, and billions of years later, spacecraft from Earth will map this terrain and recognize it as an ancient ocean basin preserved in geological amber. The air around you on ancient Mars contains the very thing that makes the ocean possible: an atmosphere thick enough to exert pressure that keeps liquid water stable on the surface. Standing here on the northern plains, you can feel the atmospheric pressure around you, not as heavy as Earth's sea level pressure, but substantial enough to notice. The pressure is perhaps half an Earth atmosphere or more, enough to prevent water from immediately boiling away into vapor when exposed at the surface. This pressure is hundreds of times greater than the thin atmosphere that will surround Mars billions of years from now. Breathing this ancient Martian atmosphere would not be possible for a human without equipment, because the composition is wrong, dominated by carbon dioxide rather than oxygen and nitrogen, like Earth's air. The air is about 95% carbon dioxide, with small amounts of nitrogen, argon, water vapor, and traces of other gases. Carbon dioxide is a greenhouse gas, and its presence in the atmosphere helps trap heat from the sun and keep the surface warmer than it would be otherwise. Without this greenhouse effect, Mars would be far colder and any water would freeze solid. Looking up at the sky, you can see clouds drifting across the pale orange expanse, and these clouds are likely composed of water vapor that has condensed into tiny droplets or ice crystals. The presence of clouds shows that water is evaporating from the ocean and entering the atmosphere, where it can be transported by winds to other parts of the planet. Some of this atmospheric water will condense and fall as precipitation, either rain or snow, depending on temperature and altitude. The precipitation feeds the valley networks that carry water back down to the ocean, completing the water cycle. The temperature here is cool but not freezing, maintaining conditions where water can exist as a liquid. Temperatures on ancient Mars probably varied significantly with location and season, with some regions experiencing freezing conditions while others remained above the freezing point. The northern lowlands during summer might reach temperatures around 5 to 15 degrees Celsius, while winter could bring temperatures below freezing, with ice forming on the ocean surface and frost appearing on the land. The global average temperature was likely somewhere around 0 degrees Celsius, hovering near the freezing point, but warm enough during favorable times and places for liquid water to persist. The source of warmth is the sun, though Mars receives less solar energy than Earth does because of its greater distance from the sun. Mars orbits at about 1.5 astronomical units on average, meaning it is 50% farther from the sun than Earth is. The intensity of sunlight follows an inverse square law. So at Mars's distance, the sunlight is about 44% as intense as at Earth's distance. This reduced solar input means Mars is fundamentally a colder planet than Earth, and maintaining temperatures warm enough for liquid water requires help from the greenhouse effect and possibly other warming mechanisms. The greenhouse effect works through the interaction between sunlight and atmospheric gases. Sunlight passes through the atmosphere and warms the surface, and the warm surface radiates heat back towards space in the form of infrared radiation. Greenhouse gases, like carbon dioxide, absorb some of this infrared radiation instead of letting it escape directly to space, and they re-radiate the energy in all directions, including back down toward the surface. This process traps heat in the lower atmosphere and at the surface, maintaining warmer temperatures than would exist if the heat could escape freely to space. The amount of greenhouse warming depends on the concentration of greenhouse gases and the thickness of the atmosphere. Ancient Mars's atmosphere needed to be much thicker than modern Mars's to provide enough greenhouse warming to keep water liquid. Estimates suggest that the ancient atmospheric pressure was somewhere between 0.5 and 2 bars, compared to modern Mars's pressure of about 0.006 bars. This represents a factor of 100 to 300 times more atmospheric mass in the past. The exact pressure is uncertain and remains a subject of scientific investigation and debate. The atmosphere is maintained by a balance between sources that add gases and sinks that remove them. Volcanic activity releases gases, including carbon dioxide, water vapor, and sulfur dioxide from Mars's interior, replenishing the atmosphere over time. Impacts from comets and asteroids can also add volatiles if the impactors contain ice or carbon compounds. These sources build up the atmosphere gradually, as long as they are active. However, gases can also be lost through various mechanisms that remove atmospheric particles to space, or lock them away in rocks and ice. One crucial factor in maintaining a thick atmosphere is the presence of a magnetic field, and early Mars likely had a global magnetic field generated by convection in its liquid iron core. A magnetic field creates a protective barrier around the planet that deflects the solar wind, the stream of charged particles flowing outward from the sun. Without this protection, solar wind particles can interact directly with the upper atmosphere, stripping away gases through a process called atmospheric sputtering. The magnetic field helps shield the atmosphere from this loss, allowing it to remain thick even though loss processes are operating. Evidence for an ancient Martian magnetic field comes from measurements of crustal magnetization, where rocks in Mars's southern highlands show strong magnetic signatures, indicating they formed in the presence of a global magnetic field and locked in that magnetization as they cooled. The northern lowlands show much weaker magnetization, suggesting that by the time their surface rocks formed, the global magnetic field had already weakened or disappeared. The shutdown of the magnetic field is dated to approximately 4 billion years ago, coinciding roughly with the end of the period when thick atmosphere and surface water were most prevalent. The wind you feel on the basin floor is driven by temperature differences in the atmosphere, causing air to circulate from high-pressure areas to low-pressure areas. The Coriolis effect from Mars's rotation deflects moving air, creating weather patterns and wind systems similar in principle to Earth's, though different in detail because of Mars's different size, rotation rate, and distance from the Sun. The winds carry water vapor from the ocean to inland areas and transport dust and heat around the planet, creating weather and climate variations across different regions and seasons. Seasonal changes happen on Mars as on Earth because the planet's rotation axis is tilted relative to its orbital plane around the Sun. The axial tilt is currently about 25 degrees, similar to Earth's 23.5 degrees. And this tilt causes different latitudes to receive different amounts of sunlight during different parts of the year. Summer in the northern hemisphere brings longer days and more direct sunlight to the northern ocean, while winter brings shorter days and less sunlight. These seasonal variations affect temperature, ice formation, and atmospheric circulation, creating a dynamic rather than static environment. Water vapor in the atmosphere can move to the polar regions during winter and freeze out as ice, accumulating in polar ice caps that grow during winter and shrink during summer. This seasonal exchange between atmospheric water vapor and surface ice represents part of the Martian water budget, the accounting of where water exists at any given time. Some water is in the ocean, some is in the atmosphere, some is frozen in polar caps, and some is locked in the ground as permafrost. The total amount of water is conserved over short timescales, but the distribution among these reservoirs changes with seasons and with longer-term climate shifts. The ancient atmosphere provided not just pressure and warmth, but also protection from harmful ultraviolet radiation from the sun. Ozone, a form of oxygen with 3 atoms per molecule instead of 2, can absorb UV radiation and shield the surface. However, Mars's ancient atmosphere might not have contained much ozone if oxygen levels were low. Some UV radiation would have reached the surface, potentially limiting where and whether life could have existed if any organisms were present. The UV radiation would also drive chemical reactions in the atmosphere and on the surface, breaking apart molecules and creating new compounds. Dust is present in the ancient Martian atmosphere, just as it is in the modern atmosphere, lifted from the surface by wind and suspended in the air. The dust scatters sunlight, creating the orange-tan sky color you see above. During large dust storms, the sky can become much darker and hazier as dust concentrations increase, blocking sunlight and affecting surface temperatures. Ancient Mars likely experienced dust storms just as modern Mars does, though the thicker atmosphere might have produced different storm dynamics, including both more powerful winds capable of lifting more dust, and also heavier air that resisted the formation of global dust. Storms. The atmospheric composition and pressure you are experiencing during this ancient period are the result of billions of years of Mars's evolution since its formation. 4.5 billion years ago, early in its history, Mars would have been much hotter from the energy of formation and from radioactive decay of elements in its interior. This heat drove volcanic activity that released gases to build an early atmosphere. As Mars cooled over time, volcanic activity declined and atmospheric replenishment slowed. The changing balance between sources and sinks of atmospheric gases controlled how thick the atmosphere remained and for how long. Looking around at the landscape under this ancient atmosphere, everything appears slightly different than it would under the thin, modern Martian atmosphere. The light is softer, diffused by more air and dust particles. Distant features are hazier, obscured by atmospheric scattering that reduces visibility compared to the incredibly clear views possible through modern Mars's near vacuum. Sounds would carry better in this thicker air, though there is little to create sound in this landscape other than wind. The environment feels more substantial, more Earth-like in some ways, though still distinctly alien in color and composition. Time has moved forward now, and you are standing in the same location on the northern plains, but hundreds of millions of years have passed. The ocean still exists behind you to the north, though changes are beginning that will eventually drain it. The most significant change is one you cannot see directly, but that has profound consequences for everything else. Mars's global magnetic field has weakened and finally shut down completely, and the planet now orbits the Sun without the protective magnetic shield that once deflected the solar wind away from the upper atmosphere. The shutdown of the magnetic field happened because Mars's core cooled enough that convection stopped, and without convection, there was no longer a dynamo to generate the field. Smaller planets cool faster than larger ones because they have more surface area relative to their volume, allowing heat to escape more efficiently. Mars is about half Earth's diameter and only about 11% of Earth's mass, small enough that its interior heat dissipated more quickly. The core solidified or at least stopped convecting vigorously enough to maintain the magnetic field. And once the field disappeared, the atmosphere became vulnerable to erosion by the solar wind. The solar wind is a continuous stream of charged particles, mostly protons and electrons, flowing outward from the sun in all directions. These particles carry energy and momentum, and when they interact with a planetary atmosphere, they can transfer that energy to atmospheric particles and potentially knock them free from the planet's gravitational pull. On Earth, the magnetic field deflects most solar wind particles around the planet, preventing them from reaching the upper atmosphere directly. On Mars, without its magnetic field, the solar wind particles can penetrate to the upper atmosphere and interact with gas molecules there. The process of atmospheric loss through solar wind interaction is complex and involves several different mechanisms. One mechanism is called sputtering, where energetic solar wind particles collide with atmospheric molecules and transfer enough energy to eject them from the atmosphere into space. Another mechanism involves ionization, where solar wind particles or solar ultraviolet radiation strip electrons from atmospheric molecules, creating ions. These ions can be picked up by the solar wind's magnetic field and carried away from Mars along the field lines, a process called ion pickup. Standing on the surface, you cannot directly observe these processes happening far overhead in the upper atmosphere, but the consequences will play out over the next hundreds of millions of years. The atmospheric pressure is beginning a slow decline, dropping imperceptibly at first, but accelerating over time. The current pressure is still enough to maintain liquid water, but the trend has begun and will not reverse. Each ion or atom lost to space is one fewer particle in the atmosphere, and as the atmospheric mass decreases, the pressure drops correspondingly. Another change that is becoming more apparent is the decline in volcanic activity. Mars's cooling interior means that magma generation in the mantle is slowing, and there are fewer volcanic eruptions to release gases that would replenish the atmosphere. Earlier in Mars's history, volcanoes like those in the Tharsis region or Elysium were more active, erupting lava and releasing carbon dioxide, water vapor, and sulfur dioxide into the atmosphere. This volcanic outgassing helped maintain atmospheric thickness even as some gases were being lost to space. With volcanic activity declining, the balance shifts toward net atmospheric loss. The ocean behind you shows signs of these changes in subtle ways. Ice is more common at the surface during winter, forming in thicker layers that persist longer into the spring than they did in earlier times. The water level might be slightly lower than it was hundreds of millions of years ago, though the change is too gradual to notice in a human lifetime, or even in thousands of years. Some water is being lost from the atmosphere, as hydrogen and oxygen atoms are stripped away into space after water molecules are broken apart by solar radiation. This water loss is slow but cumulative, removing molecules one by one, but adding up over geological time. The temperature is cooler on average than it was during the earlier period, with colder winters and summers that are less warm than before. The greenhouse effect is weakening as atmospheric pressure drops, allowing more heat to escape to space. rather than being trapped near the surface. The decrease in temperature means that water is less stable as a liquid, and more regions are experiencing freezing conditions more of the time. The ocean still exists, but its extent is beginning to shrink as ice accumulates at the poles and permafrost forms in the ground, locking water away in solid form rather than keeping it in the liquid reservoir. Walking back toward the shoreline that you visited in the ancient past shows that the water's edge has moved. The shoreline is now at a lower elevation than it was before, exposing areas of the basin floor that were previously underwater. The beach you walked along is now farther inland, and a new beach has formed at the lower water level. The change represents the beginning of the ocean's retreat, a process that will continue as water is lost to space, frozen in ice caps, or sequestered as ground ice. The total volume of liquid water in the ocean is decreasing century by century, millennium by millennium. The atmosphere still feels substantial around you, thicker than modern Mars, but thinner than it was during the ocean's peak. The pressure is perhaps 300 or 400 pascals now, compared to perhaps 600 or 800 pascals during the earlier period. A subtle decrease that affects water's stability. At some threshold pressure, liquid water can no longer exist on the surface because the atmospheric pressure drops below the triple point of water, the combination of temperature and pressure, where water can exist as solid, liquid, or vapor. Below the triple point pressure of 611 pascals, water either freezes or sublimates directly from ice to vapor without passing through the liquid phase. The sky above shows fewer clouds than before, indicating that less water is evaporating into the atmosphere and that the atmosphere is less able to hold moisture. The water cycle is weakening as the climate cools and dries, with less evaporation from the ocean, less atmospheric transport of water vapor, and less precipitation falling on the highlands. The valley networks are still flowing, but with reduced discharge, carrying less water than they did during wetter periods. Some smaller valleys may have stopped flowing entirely, their channels now dry most of the time with water, flowing only during occasional wet periods or localized storms. The transition you are witnessing is gradual rather than sudden, taking place over tens to hundreds of millions of years rather than in a quick catastrophe. Mars is not experiencing a sudden climate shift, but rather a slow cooling and drying, driven by the loss of atmospheric mass and the decline of volcanic activity. The ocean will not disappear overnight, but will instead shrink slowly as water is removed by various processes. Some water will escape to space, some will freeze into polar ice caps that grow over time, and some will soak into the ground and freeze as permafrost beneath the surface. Evidence from modern Mars supports this picture of gradual change. Different regions show minerals that formed under different water availability conditions, suggesting that the climate varied over time and space. Some areas have minerals indicating abundant liquid water, while others show minerals suggesting less water or colder conditions. The valley networks show different ages based on crater counts, indicating that they formed over an extended period rather than all at once. The geological record preserves a history of changing conditions rather than a single static environment. The solar wind continues its relentless interaction with the upper atmosphere, and without the magnetic field to deflect it, the atmospheric loss will continue until the atmosphere thins to a small fraction of its current density. Modern spacecraft measurements show that Mars is currently losing about 100 grams of atmosphere per second to space, primarily oxygen and hydrogen atoms from water molecules that have been broken apart. In the past, when the solar wind was stronger and the atmosphere was thicker, the loss rates were likely higher, perhaps several times the modern rate. Looking out across the landscape, the changes are subtle but real. The air is thinner, the temperature cooler, the ocean smaller, and the water cycle weaker than before. Mars is in transition from a world where water is relatively common at the surface to a world where water will be rare and mostly frozen. The timeline for this transition is measured in hundreds of millions of years, a timescale so long that continents drift and mountains erode on Earth, but during which Mars slowly dries out. You are witnessing the early stages of the process that will eventually transform Mars into the frozen desert that humans will encounter when their robotic explorers arrive billions of years in the future. More time has passed, and now you stand in a Mars that has changed profoundly from the ocean world of the distant past. The northern lowlands are still before you, but where water once stretched to the horizon, there is now mostly ice and exposed basin floor. The ocean has not disappeared entirely, but it has shrunk to a fraction of its former size, retreating northward and downward into the deepest parts of the basin. The atmosphere above is thin enough now that you can feel the difference, a pressure barely sufficient to sustain any liquid water, and dropping year by year toward the threshold where liquid water cannot exist at all. The water that has left the ocean has gone to several different destinations, each pathway removing molecules from the liquid reservoir and locking them away in other forms. A significant portion has escaped to space entirely, lost forever from Mars through the atmospheric stripping processes that have been operating for hundreds of millions of years. Water molecules in the atmosphere are broken apart by solar ultraviolet radiation, splitting H2O into hydrogen and oxygen. The hydrogen is very light, and some of it escapes Mars's gravity directly because the planet is small and its gravity relatively weak. The oxygen, being heavier, escapes more slowly, but still gets removed through interaction with the solar wind. Another major destination for the missing water is the polar ice caps, which have grown substantially as water vapor has been transported poleward by atmospheric circulation and deposited as ice. The North Polar Cap and South Polar Cap have accumulated layers of water ice mixed with dust and seasonal carbon dioxide frost, building up deposits that are now kilometers thick in their central regions. The polar caps represent a long-term storage reservoir for water, holding it frozen in place where the temperature never rises high enough for it to melt and return to the liquid phase. As long as Mars remains cold, the ice caps will persist and continue to grow if water remains available in the atmosphere. A third destination is the ground itself, where water has soaked into the porous soil and rock and frozen as permafrost, ice mixed with soil particles. Permafrost forms when the ground temperature remains below freezing year-round, and Mars's cooling climate has pushed the permafrost zone downward in latitude and upward to shallower depths beneath the surface. Water that infiltrates into the ground during brief warm periods or from the bottom of the shrinking ocean freezes in place and becomes locked in the subsurface, no longer available to participate in the surface water cycle. The volume of water stored as permafrost is difficult to estimate, but might rival or exceed the amount in the polar caps. The remaining liquid water exists now only in isolated lakes in the deepest parts of the northern lowlands, sheltered locations where the combination of elevation, temperature, and pressure still allows water to remain liquid at least part of the time. These lakes are far smaller than the original ocean, perhaps only hundreds of kilometers across rather than thousands, and their existence is precarious. During winter, they freeze solid, and during summer, they might partially melt, creating temporary liquid zones before freezing again. The lake ice is thick, perhaps meters deep, and only the deepest parts of the lakes maintain liquid water beneath the ice cover. Walking across what was once ocean floor shows you a landscape transformed by the water's departure. The exposed basin floor is covered with sediment that was deposited when this area was underwater. But that sediment is now dry and in places is being eroded by wind. The wind picks up fine dust and sand, transporting it across the landscape and slowly wearing down the surface features that the ocean created. Some areas show frost or thin ice layers, water that has frozen on the surface during the cold nights and partially sublimates during the day. The frost appears white against the reddish-brown soil, creating patterns that shift with the daily temperature cycle. The shoreline features that marked the ocean's maximum extent are still visible in the landscape, preserved as beach ridges and wave-cut terraces that are now stranded high above any remaining water. These features are no longer being actively formed because the water level has dropped so far below them, but they remain as geological evidence of where the water once stood. Future observers examining these features will be able to reconstruct the ocean's size and shape by mapping where the shorelines run and what elevation they occupy. The shorelines are like bathtub rings, marking the former water level on the landscape. The valley networks that once fed the ocean are now dry in most places, their channels empty of flowing water. The streams that carved these valleys stopped flowing when the rainfall ceased and the groundwater table dropped below the level where springs could discharge to the surface. The valleys remain as channels cut into the rock, showing the same meanders and tributaries they had when water flowed through them, but now they are static features rather than active river systems. Occasionally, during unusual warm periods, or when subsurface ice melts, water might flow briefly in some channels, but these events are rare and short-lived compared to the continuous flow of the past. Looking at one of the isolated lakes that still exists, you can see that its surface is mostly frozen, with ice covering all but perhaps a small area in the deepest center, where water remains liquid beneath an ice lid. The ice surface appears rough and fractured, showing pressure ridges where ice sheets have pushed against each other and cracked under stress. The color of the ice is slightly dirty, incorporating dust and sediment from the atmosphere and from the lake bottom, giving it a tan or brown tint rather than the pure white of clean ice. The lake edges are not clearly defined because ice gradually transitions to frozen ground, making it difficult to say exactly where the lake ends and the land begins. The atmospheric pressure here is now very close to the triple point of water, hovering around 600 to 800 pascals, depending on elevation and local conditions. At this pressure, liquid water is barely stable and can exist only within a narrow temperature range very close to 0 degrees Celsius. If the temperature rises above a few degrees, the water tends to evaporate or boil rather than remaining liquid. If the temperature falls below 0, it freezes. The margin for liquid water is disappearing, and within another few 100 million years, or perhaps sooner, Liquid water will no longer be able to exist on the Martian surface at all, except perhaps in the most sheltered locations during brief warm periods. The loss of the ocean has affected the entire Martian climate system. With less water vapor in the atmosphere, there are fewer clouds and less precipitation. The water cycle has broken down from a robust system involving evaporation, atmospheric transport, precipitation, and runoff into a weak system where most water is frozen and only small amounts move between ice reservoirs through atmospheric vapor. The lack of atmospheric water vapor also reduces the greenhouse effect, because water vapor is a greenhouse gas, contributing to a feedback loop where cooling leads to less water vapor, which leads to more cooling, which leads to even less water vapor. The planet's albedo, its reflectivity, has increased as ice and frost become more common, and as the ocean disappears. Ice and frost reflect more sunlight than dark water or rock, meaning more solar energy is reflected back to space rather than being absorbed and warming the surface. This increased albedo contributes another cooling feedback, where ice formation increases reflectivity, which reduces absorbed solar energy, which cools the surface further, which allows more ice to form. These positive feedbacks, where a change amplifies itself rather than reversing, have helped drive Mars from a relatively warm, wet state to a cold, dry state. Some scientists studying modern Mars have proposed that even after the main ocean disappeared, there might have been episodic periods when water briefly returned to the surface. Volcanic eruptions could release water vapor and temporarily thicken the atmosphere, or impacts from water-rich comets could add water and create temporary atmospheric thickening. These events might create conditions where liquid water could exist for thousands or tens of thousands of years before freezing or evaporating again. The geological record might show evidence of these episodic wet periods superimposed on the overall trend toward dryness. The current era you are witnessing is sometimes called the Hesperian period, following the earlier Noachian period when the ocean was at its peak. The Hesperian lasted from approximately 3.7 billion years ago to about 3 billion years ago, spanning the time when water was leaving the surface and Mars was transitioning from wet to dry. The later Amazonian period, from 3 billion years ago to the present, represents the long dry phase when Mars has been essentially frozen, with only minor water activity compared to the earlier periods. Walking north toward where the remaining lake ice exists, you can see the exposed sedimentary layers in low ridges and scarps where erosion has cut into the basin fill. The layers appear as horizontal bands in different colors, each layer representing a different time period when sediment was depositing in the ancient ocean. The layers near the top are the youngest, deposited last before the ocean retreated, while layers deeper down are progressively older. Reading the layers like pages in a book would tell the story of the ocean's history, recording changes in sediment sources, depositional environments, and water chemistry over millions of years. The transformation from ocean world to frozen desert is nearly complete at this point in time, and the remaining water is concentrated in ice caps and ground ice rather than in liquid form. The Mars that humans will eventually explore with rovers and landers is approaching. A cold, dry world where water exists, but almost entirely as ice. The traces of the ocean will remain in the geological record, waiting for careful observers to recognize them and reconstruct what was lost. The evidence will include the shorelines, the sediments, the valley networks, and the mineralogy that requires water to form. All preserved because Mars's low erosion rates and geological stability allow features to persist for billions of years. The passage of time has brought you to the present day, and you are now standing on modern Mars as it exists when human spacecraft first begin to explore it. The northern lowlands stretch around you exactly as they did in the ancient past, but the ocean that once filled them is long gone. The surface beneath your feet is cold, far below freezing at a temperature of perhaps minus 60 degrees Celsius on an average day. The sky above is a pale butterscotch color, lighter than the orange tan of ancient Mars, because the atmosphere is so thin now that dust is less concentrated, despite being easily lifted by winds. The atmospheric pressure at your current location is approximately 600 pascals, less than 1% of Earth's sea level pressure, and right at the edge of water's triple point. At this pressure, liquid water cannot stably exist because the boiling point and freezing point meet, leaving only ice and water vapor as possible phases. If you were to somehow create liquid water here, it would either freeze instantly if the temperature is below 0 Celsius, or boil and evaporate immediately if the temperature is above 0. The thin atmosphere that was once thick enough to support an ocean is now barely present, reduced to a whisper of carbon dioxide. Looking around at the landscape, you see flat terrain extending in all directions, with subtle undulations and low ridges breaking the monotony. The surface is covered with fine reddish dust that gives Mars its characteristic color, and scattered rocks protrude from the dust layer at irregular intervals. No water is visible anywhere, no ice on the surface in this season and location. Just dry dust and rock beneath the cold sky. The horizon is sharp and clear in the thin atmosphere, showing details many kilometers away, without the haze that thickened air would create. The temperature variations on modern Mars are extreme, with daily swings of 100 degrees Celsius or more between daytime high and nighttime low. During the day, solar heating can warm exposed surfaces to above freezing if the sun angle is favorable, perhaps reaching 0 degrees Celsius, or slightly higher in equatorial regions during summer. At night, the lack of atmospheric insulation allows heat to radiate away quickly, and temperatures plummet to minus 100 degrees Celsius or lower. No liquid water can survive this daily freeze-thaw cycle, and any ice that forms at night typically sublimates during the day without passing through a liquid phase. The northern lowlands where you stand have been mapped extensively by spacecraft orbiting Mars, and those maps reveal features that support the ancient ocean hypothesis. Elevation data shows that the northern lowlands are consistently lower than the southern highlands by about 4 to 5 kilometers, on average, creating the basin topography that water would naturally fill. The boundary between lowlands and highlands follows along elevation contours that would represent shorelines if water had filled the basin to those levels. The contact zones show characteristics similar to terrestrial shorelines, including possible beach deposits and wave-cut terraces. Thermal inertia mapping, which measures how quickly the surface changes temperature in response to heating and cooling, shows that the northern lowlands have different properties than the highlands. Materials in the lowlands tend to have lower thermal inertia, consistent with fine-grained sediments rather than bedrock. Exactly what would be expected if the lowlands were filled with sediment deposited in an ancient ocean. Some regions show higher thermal inertia in patterns that might represent ancient river deltas or other water-deposited features. Though interpreting thermal inertia requires caution, because many factors affect it, the mineralogy detected from orbit provides perhaps the strongest evidence that water once existed here. Instruments on spacecraft have identified clay minerals called phyllosilicates in various locations, including some areas of the northern lowlands and in valley networks draining into the lowlands. These clays form through chemical weathering of volcanic rock by liquid water, a process that requires sustained water presence over long time periods. The clays preserve a signature of past water, even though that water disappeared billions of years ago, because the mineral structure is stable once formed. Other minerals, including sulfates and carbonates, have also been detected in some regions of Mars, indicating different water chemistry conditions at different times or locations. Sulfates can form when water interacts with volcanic sulfur compounds, creating acidic solutions that deposit sulfate minerals when they evaporate. Carbonates form when carbon dioxide dissolves in water and reacts with calcium or other elements, a process that should have been common if Mars had a thick carbon dioxide atmosphere and surface water. The limited carbonate detection is actually puzzling because models suggest more carbonates should have formed, and their relative scarcity is still not fully explained. Walking across the basin floor, you notice that the surface is not completely uniform despite its general flatness. Some areas appear slightly darker or lighter than others, indicating different compositions or grain sizes. Some regions show patterns of polygons a few meters across, formed by repeated freeze-thaw cycles in ground ice that create contraction cracks, similar to mud cracks but caused by ice. The polygons are subtle, visible mainly from the shadows they cast or from slight color differences along the cracks. They indicate that ice exists beneath the surface, even though none is visible on top. The subsurface ice has been detected directly by several methods. The Phoenix lander, which touched down in the northern plains in 2008, used a robotic arm to dig trenches in the soil and uncovered bright white ice just a few centimeters below the surface. The ice sublimated away over the following days as the trench exposure allowed it to interact with the atmosphere, proving it was water ice rather than salt or another bright mineral. Radar instruments on orbiting spacecraft have also detected subsurface ice by measuring how radio waves penetrate and reflect from underground layers, revealing ice deposits extending from the poles to surprisingly low latitudes. The polar ice caps are visible in the distance if you look north from where you stand, though from this latitude they might be too far below the horizon to see. The North Polar Cap is a permanent feature containing water ice mixed with layers of dust, forming a structure about 1,000 kilometers across and up to 2 kilometers thick at its center. During winter, carbon dioxide from the atmosphere freezes onto the water ice cap, adding a seasonal cap perhaps a meter thick that sublimates away again during summer. The South Polar Cap is similar but smaller, with a permanent water ice component buried beneath a surface layer of carbon dioxide ice that persists year-round. The atmosphere you are experiencing on modern Mars is not just thin, but also very dry, with water vapor making up only about 0.03% of the atmospheric composition. The total amount of water vapor in the entire atmosphere, if it were all condensed to liquid, would create a layer only about 10 to 20 micrometers thick, if spread across the planet. This is a tiny amount compared to Earth's atmosphere, which contains enough water vapor to create about 2.5 centimeters of liquid water, if condensed globally. The dryness reflects the fact that almost all of Mars's remaining water is locked in ice caps and permafrost, rather than circulating through the atmosphere. Dust is a major component of the modern Martian environment, and dust storms are common events that can grow to planetary scale under the right conditions. The thin atmosphere might seem incapable of lifting dust, but wind speeds can be very high because the low air density means less force is needed to accelerate the air to high velocity. Dust devils, small whirlwinds that pick up dust and carry it upward, are frequently observed by landers and rovers. Larger dust storms can cover entire regions and occasionally grow to encircle the planet, blocking sunlight and altering surface temperatures for weeks or months until the dust settles. Looking at orbital images of the region where you stand shows features that modern researchers have interpreted as evidence of the ancient ocean. Channels and valleys that appear to drain into the lowlands from the highlands are visible in high-resolution images, showing braided patterns and distributary features consistent with water flow. Some researchers have identified what they interpret as ancient deltas at the mouths of these valleys, places where sediment was deposited when flowing water entered the standing body of water in the basin. The interpretations remain somewhat controversial because wind and other processes can create similar features, but the overall pattern supports the ocean hypothesis. The Arabia shoreline contact that you stood on billions of years ago, when water lapped at the coast, is still present in the landscape, though now it appears as a subtle change in slope or terrain, roughness, rather than an obvious beach. Detailed elevation mapping shows that this contact follows a line of consistent elevation around much of the northern basin, exactly as a shoreline should. The deuteronulus contact, representing a lower water level, is also visible at a different elevation. These contacts are not perfect lines, because post-ocean geological processes have modified them. But the overall pattern is clear enough that researchers can trace them for thousands of kilometers. The valley networks that fed the ocean are now completely dry, their channels visible as networks of winding troughs cutting through the highlands. High-resolution images from orbiters show that the valleys have the characteristics expected of water-carved channels, including meanders, tributaries, and variation in channel width. Crater, counting on the valley floors and walls, indicates that most valleys formed between 3.8 and 3.9 billion years ago, during the late Noachian period when the ocean likely existed. Since that time, the valleys have been modified mainly by impact cratering and limited wind erosion, but their fundamental form remains. Standing on this dry basin floor, knowing what was here in the past creates a connection between ancient Mars and modern Mars, between the world as it was and the world as it is. The transformation from ocean to desert took hundreds of millions of years and involved complex interactions between atmosphere, surface, and interior processes. The loss was not sudden, but rather gradual, a slow bleeding away of water and air until Mars reached the state that will persist for the remainder of its existence, unless something changes dramatically. The evidence of what was lost remains written in the rocks and landforms, waiting to be read by anyone who knows how to look. Leaving the flat northern plains and walking into one of the valley networks that once carried water down to the ocean brings you into a landscape that shows both its past and present simultaneously. The valley walls rise on either side, carved into the ancient highlands by flowing water that no longer exists. The channel floor is covered with dust and sand that has accumulated since the water stopped flowing. But beneath that modern material lies the bedrock shaped by millions of years of stream erosion. The valley's form preserves its history, even though its function has ceased. The valley you are walking through might be part of one of the larger systems that drain significant areas of the southern highlands, or it might be a smaller tributary feeding into a larger network. Either way, the characteristics are similar, with a channel that shows meandering curves and varying width as it descends toward the northern lowlands. The depth of the valley below the surrounding terrain is perhaps 50 to 100 meters, enough to create a sheltered environment that differs from the exposed plains. The valley walls provide some protection from wind, and dust accumulates more deeply here than on the exposed surfaces above. The dryness is absolute, with no sign of moisture anywhere in the channel. No ice is visible on the surface, though ice might exist beneath the dust layer if you could dig down far enough. The temperature is well below freezing, and the atmospheric pressure is too low for liquid water, so any water here can exist only as buried ice or as vapor. The vapor content is so low that frost formation is rare, except during the coldest nights in specific seasons. The valley that once flowed with water now sits frozen and still. Its active phase ended billions of years ago. Walking along the valley floor, you can see where the modern processes are slowly modifying the ancient landscape. Wind-blown sand accumulates in drifts along the valley walls, where turbulence deposits it, creating ripples and small dunes that shift with the wind direction. Dust devils occasionally sweep through the valley, visible as swirling columns of dust that move along the channel before dissipating. These small-scale wind features are erosion agents, but they work so slowly that millions of years might be required to significantly alter the valley's form. The valley walls show layering in the exposed rock, with different colored bands representing different depositional or volcanic events in Mars's past. Some layers are more resistant to erosion and form small ledges or overhangs, while softer layers erode back to form slopes. The layering is approximately horizontal, indicating that these rocks were deposited as flat layers before the valley cut through them. The valley's erosion has created a natural cross-section through Mars's geological history, exposing rocks that might otherwise remain buried. Looking closely at the valley floor, you can see evidence of the channel's former function in the smoothed bedrock and the distribution of scattered rocks. The bedrock shows polish and grooves in places where flowing water and transported sediment abraded the surface over long time periods. The rocks scattered across the valley floor vary in size from small pebbles to larger boulders, and they show varying degrees of rounding. Rounder rocks were likely transported farther by water and tumbled more, wearing down their edges, while more angular rocks might have been transported shorter distances or might have fallen from the valley walls after water flow ceased. Tributary valleys join the main valley from both sides, their smaller channels merging into the main flow path. The tributaries are typically narrower and shallower than the main valley, and some show less development, suggesting they carried water for shorter periods or with less discharge. The pattern of tributaries branching off from the main channel and themselves splitting into smaller branches creates the dendritic pattern characteristic of water-carved drainage systems. This pattern is diagnostic of erosion by rainfall or groundwater discharge rather than by other processes like lava flow or glaciation. Following the valley downstream takes you gradually lower in elevation as the channel descends toward the northern lowlands. The gradient is gentle but persistent, perhaps dropping 1 or 2 meters per kilometer of horizontal distance. This gentle slope was sufficient to maintain water flow when the valley was active, and it created the slow, steady flow that carved the meandering channel rather than cutting a steep, straight gorge. The relationship between slope, discharge, and sediment transport determines what form a river takes, and this valley's form suggests moderate discharge over extended time periods. The modern state of the valley as a dry channel is representative of the vast majority of Martian valleys, with only very rare exceptions showing any evidence of recent or ongoing water activity. Some steep slopes show dark streaks, called recurring slope lineae, that appear during warm seasons and fade during cold seasons. And these might indicate very small amounts of liquid water or wet soil flowing down slope under specific conditions. However, these features are controversial and their origin is still debated, with some researchers proposing dry sand flows rather than water as the explanation. High-resolution orbital imagery of this valley, and others like it, shows details down to the scale of individual boulders and small channels. The images reveal that the valley floor is not smooth, but rather shows texture from rocks, drifts of dust, and occasional small impact craters that formed since the valley stopped flowing. The images also show that some valley walls have gullies cutting down them, small channels that might have formed from more recent processes, including possible snowmelt or ground ice melting during brief warm periods. Though again, the interpretations are debated. The preservation of these valleys over billions of years is remarkable and reflects Mars's relatively quiet geological history since the early period of valley formation. On Earth, tectonic activity would have deformed or destroyed such features through mountain building, subduction, or volcanism. Weathering and erosion from rain, ice, and vegetation would have modified the valleys extensively. But Mars has experienced minimal tectonic activity since its early history, and the lack of liquid water and vegetation means weathering proceeds very slowly. The valleys are geological fossils preserved in a landscape that changes only gradually. Crater, counting on the valley floors and walls, provides age estimates for when the valleys formed. Scientists count how many impact craters of different sizes exist in a given area, and they compare this to models of how fast craters accumulate over time, based on the flux of impacting asteroids and comets. The crater counts suggest that most valley networks in the southern highlands formed during the late Noachian period, roughly 3.8 to 3.9 billion years ago. Since that time, new craters have accumulated on the valley surfaces, but the valleys themselves have not been actively modified by water. The question of exactly how the valleys formed remains a topic of research and debate. The valley characteristics suggest formation by sustained water flow over millions of years, but the source of that water is uncertain. Some researchers propose that rainfall was common during the Noachian period, with precipitation feeding streams that carved the valleys. Others suggest that groundwater discharge was the primary source, with aquifers releasing water through springs that fed the streams. A third possibility is that snowfall and subsequent melting provided the water, perhaps during periods of different orbital configuration, when Mars's axial tilt caused different climate conditions. Each water source mechanism has implications for Mars's ancient climate Rainfall requires a relatively warm atmosphere with active evaporation and precipitation cycles, suggesting a climate more Earth-like than is easy to reconcile with Mars's distance from the Sun, and the faint young sun problem, where the early sun was dimmer than today. Groundwater discharge could work with a colder climate if subsurface heat or thick insulating layers allowed water to remain liquid underground, even if the surface was frozen. Snowmelt would require episodic warm periods, perhaps triggered by volcanic eruptions or orbital variations. Walking through this dry valley, you're experiencing the end state of a system that once actively transported water from the highlands to the ocean. The valley represents a connection between different parts of ancient Mars's hydrological cycle, linking the regions where water fell as precipitation or emerged from springs to the basin where it accumulated as the Northern Ocean. The valley was part of a network that functioned for millions of years during Mars's wet period, then gradually became inactive as the climate dried and water sources disappeared. Looking up the valley walls toward the surface above, you can see the transition from the sheltered valley environment to the exposed plateau. The plateau surface is more heavily cratered than the valley floor because it has been exposed to impacts for billions of years without being modified by valley formation processes. The difference in crater density between valley floor and plateau surface helps confirm that the valley is younger than the surrounding terrain, carved into older rocks by the erosive action of flowing water. The silence in the valley is complete, except for occasional wind sounds, and even those are muted in the thin atmosphere. On Earth, a valley like this would have sounds from birds, insects, flowing water, rustling vegetation, or other biological sources. But Mars's sterile surface provides none of these. The only sounds are geological, the rare pop of thermal contraction when temperature changes rapidly, or the faint whisper of wind-blown sand moving across rock. The quiet emphasizes the valley's current dead state compared to its former active state when water sounds would have been constant. Walking across the modern Martian landscape toward the north eventually brings you to a region where the surface changes from reddish dust to brighter tones, and you are approaching the edge of the North Polar ice cap. The ice cap is a permanent feature on modern Mars, a deposit of water ice mixed with dust that has accumulated over millions of years. The cap is roughly 1,000 kilometers across and reaches a maximum thickness of about 2 kilometers near its center. This ice represents water that was once part of the ancient ocean and atmosphere, now frozen and locked away in the polar regions. The edge of the ice cap appears as a transition zone where dusty surface gives way to increasingly ice-rich terrain, and eventually, the ice becomes the dominant material visible at the surface. The ice is not pure white, like fresh snow on Earth, but rather shows layers of white ice alternating with darker layers of dust, creating a banded appearance in places where the layers are exposed in cliffs or scarps. The dust layers represent periods when dust deposition from the atmosphere was particularly heavy, while the white ice layers represent periods when ice accumulation dominated over dust deposition. Standing at the ice cap edge and looking toward the center, you can see the overall dome shape of the cap rising toward its central high point. The surface is not smooth, but rather shows complex terrain, including spiral troughs that wrap around the polar region in a distinctive pattern. The troughs are valleys cut into the ice, perhaps 1 or 2 kilometers wide and several hundred meters deep, and they spiral outward from near the center of the cap in a pattern that resembles a giant pinwheel. The troughs form through a combination of ice ablation driven by winds and sunlight, with katabatic winds flowing down the ice cap slopes and eroding preferentially along certain paths. The temperature here is colder than in the equatorial regions, typically ranging from about -80 degrees Celsius to -120 degrees Celsius, depending on season. During winter, the temperature drops low enough for carbon dioxide from the atmosphere to freeze directly onto the water ice cap, forming a seasonal cap perhaps 1 to 2 meters thick. The carbon dioxide ice is whiter than the dusty water ice beneath, and it creates a temporary bright layer that sublimates away again when spring arrives and temperatures rise above carbon dioxide's sublimation point of -125 degrees Celsius. At Martian atmospheric pressure, the presence of water ice at Mars's poles has been known for decades through telescopic observations from Earth and spacecraft observations, but the thickness and detailed structure became clear only with modern orbiting radar instruments that can penetrate ice and map the layers beneath. The radar data shows that the ice cap contains distinct layers that may represent different climate periods in Mars's past, possibly related to variations in the planet's orbital parameters. Mars's axial tilt varies over timescales of hundreds of thousands to millions of years, changing how sunlight is distributed across the planet's surface and affecting where ice accumulates. Walking onto the ice cap itself requires care because the surface includes areas of solid ice that are slippery and areas where dust covers the ice, providing more traction. The ice is hard at these temperatures, as solid as rock, and it does not melt or deform easily under these conditions. Any water molecules at the surface can sublimate directly from solid ice to vapor without passing through the liquid phase. And this sublimation is what slowly erodes the ice cap over time. The rate of sublimation depends on temperature, atmospheric humidity, and sunlight exposure, with south-facing slopes sublimating faster than north-facing slopes. The layering visible in ice cap cliffs shows alternating ice and dust bands that might represent Mars's climate variations over time. Each layer potentially records information about atmospheric conditions when it formed, including how much dust was in the atmosphere, what the temperature was, and how much water vapor was available. Reading these layers is similar to reading ice cores on Earth, where scientists drill into ice sheets and analyze the ice composition, trapped air bubbles, and dust content to reconstruct past climate. Mars ice cores have not yet been obtained, but the exposed layers in trough walls provide some similar information. The volume of water in the North Polar Cap is estimated at roughly 1.2 million cubic kilometers, enough water to create a global layer about 8 meters deep if spread evenly across Mars's entire surface. The South Polar Cap contains less water, perhaps enough for an additional 2 to 3 meters of global equivalent. Together, the polar caps contain a significant fraction of Mars's current water inventory, though this is much less than the amount that existed during the ancient ocean period. Most of the original water has been lost to space or remains locked in ground ice, rather than being concentrated in the polar caps. The ice cap accumulates water during the current climate through a process where water vapor sublimates from mid-latitude ground ice during summer gets transported poleward by atmospheric circulation, and deposits as ice at the poles where temperatures are coldest. This process is very slow, adding perhaps micrometers per year on average, but over millions of years, it can build up significant ice thickness. The process works in both directions, with some ice sublimating from the polar caps and being transported equatorward. But the net flow under current conditions is toward the poles, leading to gradual ice accumulation. Looking at the polar ice cap and knowing its history creates a connection to the ancient ocean. The water molecules in this ice were once part of that ocean, evaporated into the ancient atmosphere, and eventually transported to the poles as the climate cooled. Some molecules might have made the journey directly from ocean to polar ice, while others might have spent time in other reservoirs, including ground ice, atmospheric vapor, or temporary lakes before ending up frozen at the poles. The ice cap is a repository of ancient water, holding it in storage until perhaps far in the future, if Mars's climate changes again. The layering in the ice cap suggests that Mars's climate has varied cyclically over the past several million years, likely driven by variations in orbital parameters, including eccentricity, obliquity or axial tilt, and precession of the rotation axis. These orbital variations, called Milankovitch cycles, after the scientist who studied them on Earth, affect how sunlight is distributed across a planet's surface. When Mars's obliquity is higher, more sunlight reaches the poles and less reaches the equator, potentially causing polar ice to sublimate and mid-latitudes to receive more ice deposition. When obliquity is lower, the poles become colder and ice accumulates there. Modern spacecraft observations have detected water ice, not just at the poles, but also at surprisingly low latitudes beneath the surface. The Mars Odyssey orbiter used a neutron spectrometer to detect hydrogen in the top meter of soil. And hydrogen indicates water because water molecules contain hydrogen atoms. The data showed that ice-rich soil exists poleward of about 50 or 60 degrees latitude in both hemispheres, and extends to lower latitudes in some regions. This ground ice represents another reservoir of water, smaller than the polar caps, but distributed over a large area and potentially accessible for future Mars exploration. The Phoenix Lander mission in 2008 confirmed the presence of ground ice by directly digging into the soil and exposing bright white ice just a few centimeters beneath the dusty surface layer. The lander was in the northern plains at about 68 degrees latitude, well within the ice-rich zone identified by the orbital data. The ice sublimated over several days after exposure, proving it was water ice rather than salt or another bright mineral. The ice was mixed with soil rather than forming a pure layer, consistent with permafrost where ice fills the pores between soil particles. The presence of so much ice just beneath the surface raises questions about whether Mars's water budget is really as depleted as the atmospheric pressure and lack of surface water suggest. The polar caps and ground ice together might contain water equivalent to a global layer of perhaps 20 to 30 meters, far less than the 100 to 200 meters estimated for the ancient ocean, but still a substantial amount. The discrepancy represents water that was lost to space over billions of years. Hydrogen and oxygen atoms stripped from the atmosphere and carried away by the solar wind after water molecules were broken apart by solar radiation. Looking across the ice cap toward the center, You can see the permanent white dome that persists year-round, even after the seasonal carbon dioxide cap sublimates. This permanent cap is water ice, too cold to sublimate away completely under current conditions. The cap has likely been present for millions of years and will remain unless Mars's climate warms significantly, which seems unlikely without some major change, like increased volcanic activity or artificial modification by future human activities. The ice cap is a stable feature under the current cold, dry climate, slowly growing as more water is transported poleward from lower latitudes. The spiral troughs that cut through the ice cap are visible from your position as dark lines spiraling outward from the center. The troughs are thought to form through a combination of ablation driven by katabatic winds and solar radiation preferentially heating certain slopes. The spiral pattern is influenced by Mars's rotation, which deflects the winds through Coriolis effect and creates the characteristic curved pattern. The troughs are not static, but slowly migrate and evolve over thousands of years as ablation continues to reshape them. Understanding the polar ice caps helps complete the story of where the ancient ocean's water went. Some escaped to space, gone forever from Mars, except perhaps for occasional additions from impacting comets. Some is frozen in the polar caps, concentrated in the coldest regions. Some is locked in ground ice at mid to high latitudes, distributed beneath the surface, where it remains stable. And a tiny fraction remains in the atmosphere, as water vapor, too little to create weather systems like those on Earth, but enough to create morning frost in some locations and to slowly transport water between different surface reservoirs. The water cycle on modern Mars is greatly diminished compared to ancient times, but it has not stopped completely, just slowed to a glacial pace. The atmosphere surrounding you on modern Mars is profoundly different from the thick air of the ancient period when the ocean existed. Standing on the northern plains and considering the air around you, you find that the pressure is approximately 600 pascals, which is less than 1% of the atmospheric pressure at Earth's sea level. This thin atmosphere is barely enough to create weather, barely enough to scatter sunlight and create the sky color you see above. The composition is 95% carbon dioxide, 2.7% nitrogen, 1.6% argon, and only about 0.13% oxygen, with water vapor making up a tiny fraction of perhaps 0.03%. The thinness of this atmosphere means it provides almost no insulation against temperature changes, and surface temperatures can swing wildly between day and night. During the day, sunlight warms the ground and the air immediately adjacent to it. But that warmth radiates away quickly because there is so little atmosphere to trap the heat. At night, temperatures plummet as the surface cools by radiation to space, with no atmospheric blanket to slow the heat loss. The daily temperature range can exceed 100 degrees Celsius, from perhaps 10 degrees above freezing in the warmest afternoon moments at equatorial summer to minus 100 degrees Celsius or lower during winter nights. The low pressure means that liquid water is unstable at the surface, existing in a state below water's triple point, where liquid cannot form under normal conditions. The triple point pressure for water is 611 pascals, and Mars's surface pressure is typically around 600 pascals, right at the boundary. This means that any water exposed at the surface will either freeze if the temperature is below 0 Celsius, or boil and evaporate if the temperature is above 0. Water can sublimate directly from ice to vapor without melting, and this is the primary way water moves in the modern Martian environment. The carbon dioxide that dominates the atmosphere undergoes its own cycle of freezing and sublimating, particularly at the polar regions. During winter, temperatures drop low enough for carbon dioxide to freeze out of the atmosphere directly onto the surface, forming dry ice deposits. At Mars's atmospheric pressure, carbon dioxide freezes at about minus 125 degrees Celsius, and polar winters easily reach this temperature. The seasonal caps that grow at both poles during winter are primarily frozen carbon dioxide, and they can extend down to latitudes of about 60 degrees during the coldest months. When spring arrives and sunlight returns to the polar regions, the carbon dioxide ice begins to sublimate back into the atmosphere, releasing the gas that had been temporarily stored in the winter ice. This seasonal cycle creates a measurable change in the global atmospheric pressure, which increases when the poles release carbon dioxide and decreases when the poles trap it again. The total change is about 25% of the average pressure, a significant fraction that demonstrates how thin the atmosphere really is. On Earth, seasonal variations in atmospheric pressure are tiny fractions of a percent. Because the atmosphere is so massive, looking up at the sky above you, the color during daytime is not the blue you would see on Earth, but rather a butterscotch or peachy orange tone. The color comes from the dust suspended in the atmosphere, rather than from molecular scattering of blue light as on Earth. Fine dust particles are always present in the Martian atmosphere, and they scatter red and orange wavelengths more efficiently than blue at the particle sizes common on Mars. During dust storms, the sky becomes even more orange or reddish, and the sun appears as a blue or bluish-white disk, rather than yellow, because the dust removes the red light from the direct beam. The atmosphere provides almost no protection from ultraviolet radiation, and the surface receives intense ultraviolet light from the sun without any ozone layer to absorb it. Earth's ozone layer blocks most of the harmful UV radiation, but Mars has no ozone layer because it has no oxygen-rich atmosphere and no protective magnetic field to shield the upper atmosphere from solar radiation. The UV radiation reaching the Martian surface is strong enough to break down organic molecules and sterilize the surface, which is one reason that any potential Martian life would most likely exist underground, where radiation cannot penetrate. The wind on Mars can be surprisingly strong during certain seasons and conditions, but the low atmospheric density means that even fast winds exert relatively little force. Wind speeds can reach up to 100 kilometers per hour during dust storms, which sounds dramatic, but the force exerted on objects is much less than a similar wind speed on Earth, because there is so little mass in the moving air. A 100 kilometer per hour wind on Mars feels more like a gentle breeze on Earth in terms of the pressure it exerts. Dust devils are common on Mars, and they are visible as swirling columns of dust that move across the plains, much like the dust devils that form in deserts on Earth. The low gravity and thin atmosphere actually allow Martian dust devils to grow much taller than their terrestrial counterparts, sometimes reaching heights of several kilometers. Rovers on the surface have photographed these dust devils passing nearby, and the vortices sometimes clean dust off the rover's solar panels as they pass, temporarily improving power generation. The atmosphere is so thin that it provides almost no sound transmission, and the Martian surface is quieter than any place on Earth. Sound travels through vibrations in the air, but with so little air to vibrate, sounds are much fainter and do not travel far. The Perseverance rover carries microphones that have recorded sounds on Mars, and the recordings reveal a muted soundscape where nearby sounds are audible, but distant sounds quickly fade to inaudibility. The thin atmosphere absorbs high-frequency sounds more than low-frequency sounds, so the acoustic environment is strange compared to Earth, with everything sounding slightly deeper and more muffled. Standing on the surface and thinking about the atmosphere above you, you can consider how this thin envelope of gas is still slowly being lost to space. The process that began billions of years ago, when the magnetic field failed, continues today at a much reduced rate. The MAVEN spacecraft, which orbits Mars and studies its upper atmosphere, has measured the ongoing atmospheric escape and quantified how much gas Mars loses each day. The current rate is about 100 grams per second, which sounds small, but it adds up to several tons per day and thousands of tons per year. The escape mechanisms operating today are the same ones that thinned the atmosphere over billions of years. Solar wind particles impact the upper atmosphere and can impart enough energy to atmospheric molecules to allow them to escape Mars's gravity. Ultraviolet light from the sun can split molecules and ionize atoms, creating charged particles that the solar wind can then sweep away. Thermal escape occurs when lighter atoms and molecules in the upper atmosphere gain enough speed from temperature to exceed escape velocity and leave the planet entirely. The MAVEN mission has shown that atmospheric escape rates increase during solar storms, when the solar wind is stronger and carries more energy. During these events, the escape rate can increase by a factor of 10 or more, and large amounts of atmosphere are stripped away in short periods. Over billions of years, these processes have removed most of the atmosphere that Mars once possessed, transforming the planet from a world with Earth-like atmospheric pressure to the near-vacuum conditions that exist today. The carbon dioxide that dominates the modern atmosphere is relatively heavy and less prone to escape than lighter gases, like hydrogen or helium, which is why carbon dioxide remains as the dominant component. Lighter gases were preferentially lost over time, leaving the heavier gases behind. Water molecules break apart in the upper atmosphere when ultraviolet light strikes them, and the hydrogen atoms escape to space, while the oxygen either escapes or reacts with surface rocks to form oxides, which is why Mars appears red from iron oxide in the soil. The modern atmosphere retains only a tiny fraction of the water vapor that the ancient atmosphere must have contained when the ocean existed. The amount of water vapor in the current Martian atmosphere is enough to create a global layer only about 10 to 20 microns thick, if it all precipitated out, which is about 1/10 the thickness of a human hair. This is an extraordinarily small amount compared to Earth's atmosphere, which contains enough water vapor to create a global layer about 25 millimeters thick, if at all precipitated. Clouds do form in the Martian atmosphere, despite the low water content, and they appear as thin wisps of water ice or carbon dioxide ice crystals. At high altitudes, morning fogs can form in valleys and low-lying areas, particularly near the poles, where the temperature drops low enough for the small amount of water vapor to condense or freeze. These fogs dissipate quickly once sunlight warms the surface and the ice crystals sublimate back into vapor. The seasonal and daily cycles of the atmosphere create weather patterns despite the thinness of the air, and dust storms can grow from local events into planet-encircling systems that obscure the entire surface. The global dust storm of 2018 covered the entire planet and blocked sunlight from reaching the surface, which ended the Opportunity rover's mission when its solar panels could not generate power through the dust-darkened sky. These global storms demonstrate that even a thin atmosphere can transport enormous amounts of material when conditions align properly. Looking around at the landscape under this thin atmosphere, you can see how different the environment would have been under the thicker, ancient atmosphere. The thicker air would have created stronger winds, more active weather systems, and the possibility of precipitation in the form of rain or snow. The temperature would have been moderated by the greenhouse effect, keeping the surface warmer and allowing liquid water to remain stable. The pressure would have been high enough that water would not boil or freeze instantly when exposed to the air. The transformation from thick atmosphere to thin occurred over hundreds of millions of years, a timescale that is difficult to comprehend, but which allows geological processes to reshape worlds completely. The atmosphere that once supported an ocean covering the northern plains was stripped away molecule by molecule, ion by ion, over eons of solar wind bombardment and photochemical escape. What remains now is a remnant, a whisper of what existed, barely enough to create a sky, but far too little to support the liquid water that once filled the lowlands. The comparison between then and now demonstrates how dynamic planetary atmospheres can be over geological timescales, and how the loss of a magnetic field can fundamentally alter a planet's ability to retain an atmosphere. Mars serves as an example of atmospheric evolution, showing what can happen when a planet loses the protection that keeps solar wind from directly impacting the upper atmosphere. The lesson applies to understanding planetary habitability more broadly, both in our solar system and around other stars. Standing under this thin sky, breathing artificial air inside your suit because the natural air is unbreathable. You can appreciate the contrast with the ancient environment where the air might have been breathable, or at least thick enough to allow water to flow freely. The modern atmosphere is what remains after billions of years of loss, and it will continue to thin further over the coming eons unless some process replenishes it. The volcanoes that once released gases to maintain the atmosphere are now quiet, and Mars has no plate tectonics to recycle carbon and release fresh volatiles. The journey through ancient Mars and modern Mars reveals a transformation so complete that the two states seem like different planets entirely. Standing on the northern plains in your mind's eye, you can shift between the two versions of this world and see how profoundly it changed. The ancient Mars you walked at the beginning had water at the shoreline, valleys with flowing rivers, an atmosphere thick enough to keep water liquid, and a climate that might have supported life in the ocean or on the land. The modern Mars beneath your feet is frozen, dry, airless for practical purposes, and hostile to life as we know it on Earth. The transformation took hundreds of millions of years to complete, which is a long time by human standards, but a relatively brief period in planetary history. Mars formed about 4.5 billion years ago, and the ocean likely existed during the Noachian period from about 4.1 to 3.7 billion years ago. The ocean was lost over the next several hundred million years as the atmosphere thinned and the climate cooled. And by about 3 billion years ago, Mars had become essentially the dry, frozen world we see today. The change was not sudden, but gradual, happening so slowly that no observer living through it would have noticed the decline from year to year. The causes of the transformation are linked to Mars's size, which determined how quickly the planet cooled and lost its internal heat. Mars is about half the diameter of Earth and only about 11% of Earth's mass, which means it has much less internal heat to lose. Smaller bodies cool faster because they have less volume to hold heat, but relatively more surface area through which to radiate that heat away. As Mars cooled internally, its liquid iron core stopped convecting as vigorously, and the magnetic field generated by that convection weakened and eventually disappeared about 4 billion years ago. The loss of the magnetic field exposed the atmosphere to direct interaction with the solar wind, which is a stream of charged particles constantly flowing out from the sun. On Earth, the magnetic field deflects most of the solar wind around the planet, creating a protective bubble called the magnetosphere from being stripped away. Mars lacks this protection, and solar wind particles can reach the upper atmosphere directly, where they can ionize atmospheric molecules and carry them away into space. Over hundreds of millions of years, the cumulative effect of this atmospheric loss was dramatic, and the atmospheric pressure dropped from perhaps 1 bar or more down to the current value of less than 1% of that. As the atmosphere thinned, the greenhouse effect weakened and surface temperatures dropped. Water that had been stable as a liquid began to freeze or evaporate, and the hydrological cycle that had maintained rivers and the ocean broke down. Water was lost to space when solar ultraviolet light split water molecules into hydrogen and oxygen, with the light hydrogen escaping and the oxygen either escaping or oxidizing rocks on the surface. Volcanic activity also declined as the planet cooled, and the outgassing of carbon dioxide and water vapor that had helped maintain the atmosphere slowed to a trickle. On Earth, volcanic activity continuously replenishes atmospheric gases and helps maintain the thick atmosphere despite some loss to space. Mars's volcanism was active during the Noachian and Hesperian periods, but it declined significantly afterward, and no volcanic eruptions have been observed in modern times, although some features suggest activity within the last few million years. The water from the ancient ocean did not simply disappear into nothingness, and much of it remains on Mars in different forms. Some water was lost to space through atmospheric escape, broken down by ultraviolet light, and carried away by solar wind. Some water froze into the polar ice caps, where it remains today as permanent ice deposits, mixed with seasonal carbon dioxide ice. Some water soaked into the ground and froze as permafrost, and substantial amounts of subsurface ice have been detected across much of Mars's surface, particularly at higher latitudes. The total amount of water currently on Mars is estimated to be enough to cover the planet to a depth of about 20 to 30 meters if it were all melted and spread evenly. The ancient ocean contained enough water to cover the planet to a depth of about 100 to 200 meters in most estimates. This means that Mars has lost roughly 70 to 80% of its original water, with the remainder locked in ice at the poles and beneath the surface. The lost water represents a volume larger than Earth's Arctic Ocean, which was the original comparison that framed this exploration. Looking at the dry northern plains around you on modern Mars, you can see subtle features that hint at the water that once existed here. The smooth terrain suggests sediment deposition, the kind of smooth plains that form when fine material settles out of calm water. The low elevation of the northern hemisphere creates a natural basin that gravity would have filled with water if sufficient water existed on the planet. The boundaries between the northern lowlands and the southern highlands show elevation changes that match the predicted shorelines of the ancient ocean. Evidence for the ancient ocean comes from multiple sources, including the geological features you have walked through during this journey. The valley networks in the southern highlands flow toward the northern lowlands, suggesting they drained into a body of water that filled the basin. The shoreline features, identified in satellite imagery, run along consistent elevations that follow the equipotential surface expected for an ancient sea level. Minerals detected from orbit indicate water alteration of rocks in the regions that would have been coastal zones. Delta formations where valleys reach the lowlands suggest rivers deposited sediment into standing water. The debate about the ancient ocean is not completely settled, and some scientists question whether the evidence is strong enough to confirm a large standing body of water versus other possibilities like episodic flooding or extensive ground ice. The shoreline features are subtle and could potentially be explained by other processes, and the mineral evidence could reflect groundwater alteration rather than surface water. However, the weight of evidence has shifted toward accepting that a significant ocean did exist, at least during certain periods, and that Mars was once a much wetter world than it is today. The question of whether life ever existed in the ancient Martian Ocean remains unanswered, and it is one of the primary motivations for continued Mars exploration. If the ocean existed for hundreds of millions of years, with liquid water, organic molecules, and energy sources, the conditions might have been suitable for life to originate, or at least to survive if it arose elsewhere. Microbial life similar to Earth's early organisms could potentially have existed in the ocean, and if it did, traces might remain in ancient sedimentary rocks that formed at the bottom of the sea. Current and future Mars missions are searching for biosignatures, which are chemical or physical signs that life once existed. The Perseverance rover is collecting samples from ancient lake deposits that will eventually be returned to Earth for detailed analysis. The samples come from Jezero crater, which shows clear evidence of an ancient river delta that flowed into a lake about 3.5 billion years ago. If life existed in Martian water, delta and lake sediments are good places to look because they preserve organic materials and create environments where life might have thrived. The possibility of life on ancient Mars makes the loss of the ocean particularly poignant, because if life did exist, it would have faced extinction or been forced deep underground as the surface became uninhabitable. Any surface life would have needed to adapt to increasingly harsh conditions as the atmosphere thinned, temperatures dropped, and water disappeared. Life that could not adapt or migrate underground would have died out, leaving only fossils or chemical traces as evidence of its existence. The story of Mars teaches several lessons about planetary habitability and the fragility of conditions that support life. The presence of liquid water on a planetary surface requires a narrow range of conditions, including sufficient atmospheric pressure, moderate temperatures, and protection from radiation. Earth maintains these conditions through its size, which allows it to retain internal heat and generate a protective magnetic field, and through its distance from the Sun, which provides the right amount of energy for temperate conditions. Mars fell short on the size requirement, and its faster cooling led to magnetic field loss and atmospheric escape. Venus, which is similar in size to Earth, maintained its atmosphere but became too hot for liquid water because of its closer distance to the Sun and runaway greenhouse effect. The three rocky planets in the inner solar system demonstrate three different outcomes: Earth with stable liquid water, Mars with water lost to a thin atmosphere and cold temperatures, and Venus with water lost to a thick atmosphere and extreme heat. Understanding Mars's transformation helps in the search for habitable planets around other stars, because it shows that initial conditions are not sufficient to guarantee long-term habitability. A planet might have liquid water early in its history, but lose it as the planet evolves and conditions change. The presence of a magnetic field appears important for maintaining an atmosphere over billions of years, and planet size correlates with the ability to sustain that magnetic field through internal heat and core convection. The lost ocean of Mars represents one of the great changes in the solar system's history, a transformation from a world that resembled Earth in some ways to a frozen desert that resembles the Moon in others. The ocean was real, the water was liquid, and for hundreds of millions of years, Mars had a hydrological cycle with evaporation, precipitation, rivers, and a sea. All of that is gone now, stripped away by solar wind and locked into ice, leaving only the traces written in rocks and terrain for us to discover and interpret. Standing on the northern plains and thinking about what existed here billions of years ago, you can feel the passage of deep time and the impermanence of planetary conditions. The ocean that filled this basin is as gone as the dinosaurs, but unlike the dinosaurs, the ocean left a landscape shaped by its presence. The valleys that brought water to the sea, the shorelines where waves broke on beaches, the sediments that settled on the ocean floor, all remain as evidence that can be read by anyone who knows how to interpret the language of geology. The exploration of Mars continues, and each mission adds new details to our understanding of the ancient environment and what was lost. Rovers traverse the dry surface, examining rocks that formed in water. Orbiters map subsurface ice deposits that are remnants of the lost ocean, and instruments measure the ongoing atmospheric escape that continues to thin the air. The story becomes clearer with each piece of evidence, and the portrait of ancient Mars becomes more detailed and more certain. Your journey through this lost world has taken you from the ancient shoreline where water met land to the dry basin where that water once pooled, to the frozen poles where some of it remains. You have seen the thick atmosphere that kept the water liquid and the thin atmosphere that remains after most of it was lost. You have walked valleys that carried rivers and stood on plains that were ocean floor. The journey across time has shown you two Mars, one wet and potentially habitable, one dry and hostile, and the long, slow transformation that connected them. The ocean is gone, but its memory persists in every valley that flows toward the northern lowlands, in every shoreline feature that traces an ancient water level, and in every bit of ice that remains locked in the polar caps and subsurface permafrost. Mars preserves its own history because the lack of plate tectonics and the minimal erosion in the thin atmosphere leave ancient features intact. The planet is a museum of its own past, and the ocean that was larger than Earth's Arctic still leaves traces for those who come to read them. The transformation of Mars from ocean world to frozen desert took hundreds of millions of years and involved the loss of most of the planet's water and atmosphere. The journey is complete, the ocean is gone, and modern Mars is the result. The story is written in the rocks, waiting to be fully understood, and each new piece of evidence brings us closer to comprehending what happened and why. The lost ocean of ancient Mars is no longer just a hypothesis, but an accepted part of the planet's history. A chapter that began billions of years ago and ended with the world we see today.